Hey, Science 30s. Today we're going to be discussing part one of our discussion on the chemistry of acids and bases, which is chapter 1.2 of Unit B. Um, First of all, what is an acid? I mean, people tend to think they know what an acid is when you discuss one, but really to quantify an acid or a base is maybe a little tougher to the average person than you might think. Before we get involved into this conversation, I'm going to get you to watch this quick little video right up here about just what an acid is, just by pure definition, what an acid is, before we have our discussion. Otherwise, I'm going to continue right now. So first of all, acids and bases both form aqueous solutions. They are going to dissolve in water. That's what they do, and their state is always going to be indicated as aqueous. So AQ being their state of matter. Remember, there are four states of matter. There is solid, liquid, gas, but also aqueous is considered to be a state of matter. So when we're dealing with acids and bases, they're not liquids. They are, strictly speaking, they are aqueous solutions. So they always are going to be indicated with an AQ subscript beside them. A couple of things about acids and bases that kind of make them interesting. So, like if I take an acid like hydrochloric acid, HCl, that's a fairly common known acid, or say sulfuric acid, which we talked about in section 1.1 with the formation of acid rain. If you look at these substances, and if you think back to when you classified compounds, um, these acids are all comprised of non-metals. Uh, None of these substances here are metals. Hydrogen, chlorine, sulfur, oxygen. They're all non-metals. So technically speaking, these are molecular compounds. However, acids and bases do actually break up into ions. So they lead this double life because hydrogen acts as a cation. When hydrogen breaks away from an acid, it basically functions like, for lack of a better term, it functions like a metal. It breaks away as a positive cation from the substance. So acids and bases kind of have this double life where they exist as both. They are molecular, but they can actually they can dissociate into ions, which makes them very much like ionic compounds. And we know that ionic compounds, when you dissolve them in water, conduct electricity. And both acids and bases are able to conduct electricity, which is not normally something that a molecular compound can do. So kind of unusual in that respect. Um, Water, which is what they dissolve in, also leads a double life. So when we deal with water, it has a slight polarity to it, which means that when you look at water, which is H2O, and H2O right over here, the hydrogen portion of the molecule is slightly positive, and the oxygen portion of the molecule is slightly negative. So there's this sort of opposite charges that are happening in this molecular compound. And because of this, uh, water also has a double personality. It is a molecular compound, but it can also disassociate into ions, which makes it, again, fairly unique amongst molecular compounds. I mean, other than obviously acids and bases. So when water does disassociate, um, it basically breaks into two ions, which I'll be discussing in a couple seconds, which are called hydroxide, OH, a negative, and H3O positive, which is called hydronium. Before we take a look at the breakup, the ionic break apart, I guess, of water, I'm going to get you to quickly watch this video right over here about water, about the chemistry of water, because it does play an important role in how acids and bases actually function. All right, so as you just saw in the video, if you watched it, water does break apart into ions. And when water breaks into these ions, into these hydroxide, these negative hydroxide ions, and these positive hydronium ions, it produces them in equal amounts. So two water molecules will break apart essentially into one hydroxide and one hydronium ion. So if you've got pure water, you're going to have an equal amount of the two ions. But a Swedish chemist in the end of the 19th century by the name of Arrhenius, he basically discovered that when you add an acid to water, it actually upsets the balance. So what happens is you no longer get an equal amount of hydronium and hydroxide being produced. And I just want to kind of discuss why that is in fact occurring. So acids, all acids have one thing in common chemically. They all contain hydrogen. I mean, you can see there's a couple over here that are on the slide as well. Like there's hydrofluoric acid, which is HF. There's acetic acid, which is CH3COOH. There's carbonic acid, which we talked about in 1.1, H2CO3, and chlorous acid, which is HClO2. All of those acids have one thing in common chemically. They all have hydrogen. And what hydrogen does is it actually upsets the balance of this hydroxide and hydronium. And what it does is it actually gives, when it disassociates ionically, so when you put a acid in water, it breaks apart into ions. And one of the ions is going to be hydrogen. And that hydrogen is going to basically attach to water molecules that are present, which will cause more hydronium to be produced in the solution. So because all these free hydrogen ions are floating around, a lot of the water molecules that are there are just going to latch onto those hydrogens, react with them, and become hydronium. So what you'll see when you add an acid is there'll be less hydroxide and more hydronium in the solution. And this is what makes it more acidic. And this is, when we discuss this later in the unit, this is what's going to drop the pH of the solution. The pH is basically an indicator of how much hydronium is or isn't present in the solution, as we will get to later on. So other than producing more hydronium than hydroxide, what do all acids have in common? Well, this is a chart that you probably have seen before in some way, shape, or form. You would have maybe covered this in grade 9 science or in another course. But what I've drawn out here for you is just a little chart that sort of describes the differences between acids and bases. So generally speaking, when you're dealing with an acid, they are going to taste sour if you taste an acid, and there are some acidic solutions that you can't use. Vinegar, for example, would be one. There is one thing that is common to both acids and bases, which I mentioned already. They both form aqueous solutions that will conduct electricity. So there is one thing, at least, in common between acids and bases in that respect. But here's a couple of other things that are different. Acids are going to donate hydrogen ions. Now remember, hydrogen ions is basically it's H+. So basically a hydrogen ion is essentially just a single proton. So when we're dealing with hydrogen ions, we can also describe them as donating protons. So if you hear the term that an acid is donating a proton or it's donating a hydrogen ion, it's the same thing because it is the same thing. Hydrogen ions are in fact protons. So you may see the term proton donator as opposed to a hydrogen ion donator. And quite frankly, hydrogen ion donator is kind of mouthy. Proton donator to me sounds a lot easier. It rolls off the tongue a lot better. So I'm going to potentially use either one of those to describe when acids are donating either a proton or a hydrogen ion. Acids as well are going to have a pH of less than 7. They're going to turn blue litmus paper red. They're going to neutralize bases when they come in contact with a base. And they produce, as I've mentioned, they produce more hydronium in a solution than hydroxide. That is sort of one of the key distinguishing features of an acid when you add acid to water. At the same time, bases are not going to donate protons. They're going to accept protons. So in the case of water, if you put a base in with water and you've got your H2O molecule, if you take away a hydrogen away from an H2O molecule, what do you have left? Well, you have hydroxide. You have OH negative is what's going to be left behind when the base reacts with the water. So a base is going to be the opposite of what happens with the acid being added to the water. It's going to accept protons. It's going to accept hydrogen ions, which is going to cause more hydroxide to be present in the solution than hydronium. Some of the other things that distinguish an acid, or sorry, a base, they taste bitter. They're not sour. They taste bitter. They accept protons, which I just mentioned. They accept protons or hydrogen ions. They cause the pH of the solution to become higher than 7. And we are going to be discussing more about pH actually in the next video. I'll be discussing a lot more about pH in our second part of the discussion. Turns red litmus paper blue. That's another thing that it does. And then it's also going to neutralize acids, and it's going to, again, produce more hydroxide than hydronium. And one other thing that it does, there's a distinguishing characteristic of bases. They generally feel slippery. So if you actually touch a base, they have a very slippery, tactile feel to them when you interact with them. An example of a base, and the one that's on the slide here, is ammonia. Ammonia, when you add to water, is going to basically, you're going to have NH3 plus H2O. And then you're going to get out of that, you're going to get ammonium ions, which are going to be NH4s positive, and you're going to be left with hydroxide OH negative ions left behind. So that would be an example of a reaction with a base and water, and why you're getting more hydroxide in the solution as opposed to more hydronium. And again, over here, here's your distinguishing features of a base that I just discussed up on the board over there. So what happens if you put an acid and a base together? We've been discussing what happens when you put an acid in water or a base in water. But what if you put an acid and a base together? Now, I did mention that acids will neutralize bases and bases will neutralize acids. Well, this is sort of what we're getting at with this reaction. You may remember in grade 9, you may have learned about what were called neutralization reactions. We're going to take it a little bit of a step further here. There were a couple of scientists in the early 20th century, in the 1920s, Bronsted, and Lowry, who independently discovered that an acid, if it comes in contact with a base, will actually donate a hydrogen ion to the base. And basically, that's how they react. And what happens is essentially the acid becomes what we call a conjugate base. And then the base becomes a conjugate acid. And we'll discuss that reaction here in a couple of minutes. But basically what I'm describing is a very famous reaction in chemistry. And it's basically, the theory behind it is called the Bronsted-Lowry acid-base theory of acid-base reactions. And it's basically, this is where we're going to get involved with some chemical equations where you're going to actually have to write them out as part of this unit. And I'm going to give you an example here right away. Before we discuss the application of this Bronsted-Lowry acid-base theory or reaction, at this point, a couple of things that you should be keeping in mind. Number one, and you can see here my data booklet matches this slide beautifully. Look at that. The power of technology. I've got page 12 of my data booklet open right now, and if you've got it in front of you, I would encourage you to have the data booklet open for the remainder of this video. You're looking at the top half of the data booklet, and the data booklet is basically showing you the strengths of acids. The one side, the left side, are the names of the acids, and then on the right side, you're getting what are the conjugate bases that will result from the acid reacting with another base. So if I put, for example, on the top of the chart there, it's hydrochloric acid, which is HCl. If it reacts with a base, HCl will become chlorine ions. That's what it will disassociate into. And the chlorine ion, in this case, is considered to be a base. Now, you might also notice on the chart that on the left side, the strength of the acid increases the further up you go. On the right side, the strength of the conjugate base increases as you go down the chart. So there is a relationship that if I have a very strong acid, it will produce a very weak conjugate base. And if I have a very weak acid, it will produce a very strong conjugate base. So there is a relationship there, and we'll be discussing that a little bit more. Before we do that, though, quick little video for you to watch, kind of a really cool video right up here. This video is going to talk about the strongest acids known to science, some of the craziest ones out there. Although I didn't include it as part of this video, if you want to Google it, they also have a video. SciShow also has a video if you're interested in what the strongest bases are. There's another video related to bases, so if you wanted to watch them both, you could probably just Google it or search it in YouTube and just type in SciShow strongest bases and you'll find that video as well. But for now, take a look at these strongest acids just for poops and giggles, I guess. All right, well let's take a look now that you've had a chance to watch that video, or maybe you didn't. You're just wanting to get to this Bronsted-Lowry acid base theory that badly that you just didn't even want to watch the fun video. That's okay. I'm here to help you out. We're going to be discussing an example. And what I've got on this slide, and this is a great slide. This one here, if you've got the notes in front of you, pull up the notes so you can see that full size. But I'm going to walk you through kind of the process. Mine's a little different than what's in here, but it's sort of two roads that both lead to the same place. So I'm going to kind of walk you through it. So what you're going to have to be able to do at some point is you're going to have to, you might get a word equation for an acid-base reaction. So in this case, I've got a neutralization reaction between a carbonate ion and a substance known as orange 4. Well, at this point, if you're not an acid-base expert, it's going to be very difficult for you to determine at this point what the acid is. Now, there might be a couple of clues. You know that acids always have hydrogen in them. So just by looking at this, and I know a little bit about carbonate. Carbonate has a molecular formula of CO3, and it's two negative. It's a negative 2 ion. So I know that substance doesn't have hydrogen. So I'm going to make a really good wager that the carbonate's probably going to be the base, and this orange 4 substance that I have no idea what it is, it's probably going to be the acid. Now that's kind of a bad way to do it. So how are we going to make this easier? You're going to use page 12 of your data sheet. This is where this sheet comes in handy because it's got a list of all of these acids and bases. So what I'm going to look for first is I have to identify the formulas. Now I happen to know carbonate was CO3. You may not remember that or may not know that. That's okay. This chart's going to show you what it is. Now, if I look on the chart here, I'm looking for carbonate. Well, I see a hydrogen carbonate ion over here, and I can see that right beside hydrogen carbonate is another ion here. It doesn't list it, but I'm going to guess that's probably carbonate. So I got carbonate, and it's way down on the right-hand side of that chart. So that's a pretty strong base. That's a pretty strong conjugate base at this point. So we know that that is going to be a strong base if you put it in a solution. So I know that's going to be my base. I also know that this orange 4, which appears over here, here's orange 4, right about there on the chart. It's kind of hard to see, but it's right there. Orange 4 has a chemical equation or a chemical formula, pardon me, of HOR aqueous. So these are my formulas that I would need to write into my chemical equation. We know these are going to be the reactants because it's saying that we have a neutralization reaction between these two substances. I automatically know that it's going to be CO3 negative 2 aqueous plus HOR aqueous is going to give me something. Well, what's it going to give me? Well, here's where it gets real easy. Because if I look on my data sheet now, I can look at orange 4 and see what the conjugate base is. If I go from HOR across my data sheet to there, I'm going to see that my conjugate base for that is going to be OR negative aqueous. So I know that's going to become, this acid is going to produce a conjugate base OR negative. At the same time, I understand that a base, when it reacts with an acid, will become a conjugate acid. So in order for me to figure out the conjugate acid for my base, which is CO3, I'm going to go to the left and see what the acid is that it would form. And in this case, it forms a very weak acid, which is called hydrogen carbonate ions, which is going to be HCO3 negative. So now I've got my reactants. I've now calculated my products, and I just simply write the equation down at the end. So now I've got HOR aqueous plus CO3 2 negative aqueous is going to give me OR negative plus HCO3 negative. Now let's just classify these all. HOR, the orange 4 is my acid. My carbonate ion is going to be my base. My OR negative ion becomes my conjugate base because it was originally from the acid. And then my CO3, which is accepting the proton that's being donated by orange 4, is going to become my conjugate acid, which is HCO3 negative. So that's how you calculate an acid-base equation. On the next page, oh, actually, before I get to that, sorry. So here on this slide, here another great little write-up. I kind of wrote the same thing down over here, but basically, let's recap the reaction. The acid the acid HOR aqueous donates its proton or ion, or its hydrogen ion, to the base, which is carbonate, CO3 negative 2, and it forms a conjugate acid as a result. The carbonate does. It forms into a conjugate acid, which becomes HCO3 negative. The fact that HOR loses a hydrogen ion, a proton, means that it's going to become a conjugate base. It's losing the hydrogen now, so it becomes the conjugate base OR negative. So that's basically the reaction. A Bronsted-Lowry acid-base reaction is essentially this. Acid plus a base is going to yield me a conjugate base and a conjugate acid. Remember, the acid becomes the conjugate base, the base becomes the conjugate acid. All we're doing is we're swapping hydrogen. The hydrogen is just swapping from the acid to the base. So my acid becomes the base, and my base becomes the acid. That's how it works. It's actually kind of that simple. Here's a couple for you now. I would recommend you pause the video. You've got, and don't look at your notes. See if you can calculate these 4 right here. Do it. Just stop the video. Use your data sheet and see what you come up with. Let's be honest about it. See if you can actually come up with this on your own. And I'll give you a couple seconds here, and then we'll talk about it. You ready? You sure? Okay, let's take a look. Here are the answers, and they're on your slides. You can take a look at this. I'm not going to have this up on the board. I'm presuming you've got your notes in front of you at this point, hopefully. If not, pause the video, get your notes. What have you been doing? You should have your notes in front of you while the screen's way too small, or maybe you got really good eyesight. I don't know. So if I've got an acid-base reaction between oxalic acid and a fluoride ion, well, I know what my acid is because it's an acid. It says it. Oxalic acid is going to be my acid. Fluoride is going to be my base. So I can look at them on the chart here. I've got oxalic acid right here. Fluoride is right over here. So I know that fluoride is going to become hydrofluoric acid, and my oxalic acid is going to become HOOCCOO. So when I'm done, this is what the reaction should look like. I should have HOOCCOOH aqueous, I should say plus, not and, plus F negative aqueous becomes HOOCCOO negative aqueous plus HF aqueous. And again, the rest of them, take a look. I'm not going to go through all of them because you've got your notes in front of you, but they're all written down here, kind of like your little keys. Get used to this. There's going to be a lot of these kind of questions in the notes. So if you're doing this at home or you're missing class, these are great places when you're stopping the video to just try it on your own before you go ahead with the notes and see if you can actually pick up on what I'm trying to lay out for you in the videos. And if you make a mistake, well, you try again on the worksheets. But these are some good examples that are up there. To finish up, great video up here to watch. This is going to basically talk you right through these acid-base reactions. Fantastic review video on that. And to finish up, I'd like you to now go and complete the acid-base reaction worksheet just to see how well you're doing with all of this. And that's it. That's our first half of our discussion of the chemistry of acids and bases. Join me next time when we conclude our fascinating discussion about the chemistry of acids and bases on my part 2 segment. Take care, guys. See you soon.